Polynomial functions. We are basically adding more terms into functions that we've already worked with. For example, we saw linear functions. The first section of chapter 4, their format was f of x equals mx plus b. And I want to let you know that this right here, this expression would be considered a sum of two monomials. Okay, monomials, if I can even say it, are basically terms in which you have a number being multiplied to x to a certain power. And that's kind of the format of the terms that you're seeing in this general definition of a polynomial function. And we actually have the same sort of format going on with the quadratic function. The quadratic function was ax squared plus bx plus c. And so there's one additional term in the second function, the quadratic function, and that additional term is a times x squared, which is also a special type of monomial. And basically, we can continue adding terms of this format with higher and higher powers of x. I mean, there's no stopping us, when adding something like, an x cubed term. Although you would no longer have a quadratic function, you would have what's called a cubic function. But the point I'm trying to make is that you can continue adding terms of this format where it's, some sort of number being multiplied by x to a certain power. And even with something like, the number c right here, that's technically c times 1, which we could rewrite 1 as x to the power of 0. So when we continue adding these terms into the function with higher powers of x, we get a polynomial function. And the definition, the symbolic version of it at least, is given right here, where we're seeing terms of that format where it's some number times x to a certain power. Now this could be a little daunting to look at first because of the notation. We have a with some subscripts, and we have x with the powers. But don't be alarmed by that. This is really just a matter of organization. The numbers in front of x have the same subscript as their powers, just to kind of keep things organized and to let us know that that's the power associated with that term. And this would be a polynomial function written in standard form. You want to assume that the highest power goes first, and then the next highest power, and so on and so forth. And some specific examples are given below. For instance, in part A, we have f of x equals 2x plus 3. 2x is a monomial, and so is the number 3. And in the context of the definition of a polynomial function, 3 would serve as our a sub 0, not the Mortal Kombat character, by the way, and then 2 would serve as a sub 1. And keep in mind that any plain old number, such as 3, can be written as 3 times x to the power of 0. And I'm mentioning that just because of how I'm getting these subscripts here. Okay, the subscripts of these the subscripts of the coefficients match the power of the term that is associated with. All right, so that's 2x to the first times 3x to the power of 0. And so long story short, the a subscripts just represent the coefficients of your terms. Looking at part B, this is the sum of 3 monomials, negative x squared, 5x, and 1. In this case, a sub 0 is the number 1, 5 is a sub 1, and then negative 1 is a sub 2. Okay, so those are the specific coefficients that are going in front of x to these powers. And then at the tail end here, we have a sum of 4 monomials. Okay, in this case, negative 3 is a sub 0. The coefficient of x, which is 1, is a sub 1. Negative 1/5 is a sub 2. And 4 is a sub 3. So just a special note here, and this is kind of an older definition. A polynomial is a sum of monomials. Which a monomial, I'm not sure I shared this fact with you, a monomial is what happens when I go to a restaurant by myself. I just get a monomial. All right, and a binomial is when I go to a restaurant and I have no money. I buy no meal. All right, so the whole point of what we just went through is just to kind of demystify this definition here of what a polynomial function is. The notation can be a little tricky to work your way through, but hopefully I'm explaining it well enough. If not, do you guys have any questions about anything we just went through on this?
Does it count the same way when you're dealing with letters? So do you want H before K, X before Y, and so on when you're putting them in order?
The order is based on the powers. So like are you talking about like when we write it in standard form?
Well, let's say for like example B, if we had a 5y in there as well. So it would be negative x squared plus 5x plus 5y plus 1, because you put the x and the y in lettered order, I guess you would say.
Yeah, you could work your way to establishing a particular order for that. So like a two-variable polynomial function.
Yeah.
Yeah, so there would be ways to write that in a particular order. Usually you write like your term with the highest power of one variable first, and then you just continue going down according to power with that particular variable you chose to write first. And then as you go from left to right, like the powers on the first variable will decrease, but the powers on the second variable will increase. So like you might start with 5x squared and add 3x, and maybe there's like a term involving xy, and then at the tail end of that function, you would write the term only involving y squared. So I don't really have an example to put up on the screen here because we won't be working with two variable polynomials. It'll just be single variable.
Okay, thank you.
Yep, no problem. Okay, well, let's get to some terminology here. Then we'll do some classifying. So when a polynomial function is written in standard form, which all of these in A, B, and C are, highest term or highest power goes first, and then so on and so forth. This term, a sub n x to the n, is referred to as the leading term. And I'll usually write that as LT. The term at the very end, the one that does not have x written next to it, although you could, so long as you put x to the 0, is known as the constant term, or CT for short. The largest power of x in your polynomial function is called the degree, or capital D for short. The coefficient of the leading term is called the leading coefficient, or LC for short. And before I get to the rest, I'm going to point all these out in the generic version of the polynomial function. So assuming that the polynomial function is written in standard form, the term that goes first when reading it from left to right, a sub n x to the n, that's the leading term. The term at the very end, a sub 0, that's the constant term. And the leading term will always have the degree of the polynomial function, because the leading term is the one we write first, because it has, the highest power of all the monomials. And so going back to the leading term, the n, that's the power of x here, would be the degree of the polynomial function. And then the number that's in front of x with the degree, a sub n, that would be the leading coefficient. And all of these items I'm pointing out do have some pretty profound consequences on polynomial functions, particularly their graphs. So we'll actually be looking at the effects of different values of things like the degree, the leading coefficient, and so on and so forth. The constant term, that plays more of a bigger role in section 3 when we try to find what are called zeros of a polynomial function. Another important fact about polynomial functions is that the powers, and by that I mean powers on the variables, can only come from this set of numbers, 0, 1, 2, 3, 4, 5, and so on and so forth. And this is referred to as the set of whole numbers. So for example, things like x to the negative 2 power, that would not be allowed in a polynomial function because negative 2 does not come from the set of numbers. Another thing that's not allowed in a polynomial function is something like a square root, because you could rewrite that as x to the power of 1/2. And so terms involving powers like this are not allowed in a polynomial function. Moreover, we can never have variables in the denominator in a polynomial function. That refers to a different type of function known as a rational function. So for number 6, it says variables will never be in a denominator nor inside of a radical symbol for any given polynomial function. And one more fact is that the domain of every polynomial is all real numbers, much like we saw was the domain for the linear function and the quadratic function. And that all has to do with the fact, coming before 7, because we won't have any variables in the denominator, there's no possibility for division by 0, and we won't have any radicals in the polynomial function, so there's no square roots of negatives possible. All right, so it turns out that you can plug in any number you want into a polynomial function, which is why the domain is all real numbers. So what we're going to do, and we'll kind of go back and forth on this. We're going to look at a few expressions, a few functions that is, and determine whether or not it fits the format of a polynomial. And if so, we'll want to identify the leading term, degree, and so on and so forth. So we'll do a few of these together, and I'll ask that you guys work on a couple independently. Let's start with the first row. We've got negative 2x cubed plus 5x squared minus x plus 4. Okay, would you guys agree that this fits the format of a polynomial function? Yeah, it definitely has that format where it's a sum of monomials. Negative 2x cubed is a monomial, so is 5x squared minus x and positive 4. And the powers are good to look at too. Remember, the powers can only be whole numbers. 3 is a whole number, so is 2. X would have a power of 1. And if we wanted to write x with 4, x would have a power of 0. Now, it doesn't matter what the numbers in front are, just as long as the powers on x are whole numbers, we're good to go. That would be a polynomial. So, is it a polynomial? Definitely yes. The leading term, you'll notice that this is written in standard form. So the leading term would be negative 2x cubed. And keep in mind the leading term contains the degree. Okay, so the power on x in the leading term would be our degree. So that would be 3. The leading term also contains our leading coefficient. Okay, and our leading coefficient would be this negative 2. And what do you guys think the constant term would be within this polynomial function? 4. Yep, so we don't get the constant term from the leading term in most cases. So looking back at the polynomial function, the constant term is the term without any x's written next to it. In this case, that would be 4. So that's our constant term. All right, for row number 2, we've got x minus 1 times x plus 5. And at face value, it doesn't really look like it fits the format of a polynomial function. But if we play around with it a little bit, and I'll do it down here. And what I mean by play around is, there's something special that we can do with factors written next to each other like this, and that something special would be FOIL. Let's see what FOIL results in. All right, so if we FOIL this out, it's x squared plus 5x minus x minus 5. Simplifying, we get x squared plus 4x minus 5. And this would be a rewrite of what's currently in row 2. So what do you think about this now? Does the FOILed version of this fit the format of a polynomial function? Yep. All right, so that definitely is a polynomial function in disguise. So why don't you take the next 30 seconds or so to see if you can use the FOILed version to figure out the rest of the entries in this row. All right, ready? Leading term, x squared. The degree would be 2. What'd you guys put for the leading coefficient? Yep, I would put a 1 for that. Okay, that's the number in front of x squared. And then our constant term, negative 5. Any questions so far? What do you guys think about the function in row 3? X squared minus 2 all over x cubed minus 1. Does that fit the format of a polynomial function? Definitely not. So yeah, we do have a variable in the denominator. So this is a different type of function, which we'll look at later on in this chapter. But for now, it's not a polynomial, so none of these will apply. What do you guys think about the next function, the square root of x plus x to the fifth? That's a no as well, because of the square root of x. Okay, keep in mind we could rewrite the square root of x as x to the 1/2, and the issue there is that the power is not a whole number. So that's a no. So we don't really have to go through the rest of the boxes in that row. What do you think about the last one? Well, 8 would actually be an example of a polynomial function. It's kind of a special case. It is a monomial. You could write 8 as 8 times x to the 0, because x to the 0 is 1, and it fits that monomial format. So I include it in examples like this just to kind of shed some light on these special cases. 8 technically fits the format of a polynomial function, so we would put yes for this. And the leading term would just be 8. It's the only term. What do you think the degree would be? The degree would be 0. Okay, I'm getting that from here. The leading coefficient would be 8. And then the constant term would also be 8. So basically we're operating with just this one single term that makes up this function. All right, so 8 times x to the 0. It doesn't contain a lot of monomials, right? It's just a single monomial, but it does, in a roundabout way, meet the criterion for a polynomial function. And we would classify all those, typical things, accordingly. It just so happens to be that a lot of the features, such as leading term, coefficient, and constant term, involve just the number 8 itself, just due to the format. All right, any questions about the definition of a polynomial function and its features? Because if not, we're going to dive into some features of polynomial function graphs. Okay, so I want to help differentiate graphs that would represent graphs of polynomials versus graphs that would not. And there are two main features of the graphs of polynomial functions. One of them is that polynomial functions are smooth. And the best way to think about a polynomial function graph that's smooth is just to recognize that there are some nice rounded hills and rounded valleys. Okay, polynomial graphs can be very curvy. There are going to be some maximums and minimums and what have you, but where they occur are going to be, like the tops of hills or, the bottoms of valleys. And so for smooth, just think, hills and valleys. Another feature is that they're said to be continuous. And there are a couple of ways of describing, what it means for a graph to be continuous. Of those ways, I like to go with this one. When a graph is continuous, it's fully connected. Okay, so there are no gaps, there are no open circles. the graph is not broken up into different pieces, like we saw with piecewise functions. And every polynomial function graph is going to have ends, okay? And the ends of a polynomial function graph extend indefinitely. So I want to include that as maybe an additional note. We'll say the ends extend indefinitely. So that's kind of a, perhaps a third hallmark of polynomial function graphs. And in this table, I hope to illustrate all these little descriptors here. So let's look at the first column. The first column contains examples of polynomial graphs. As you can see, there's like a hill right there, nice rounded hill, nice rounded valley. Okay, these are where we would find our maximums and minimums, by the way. The graph is fully connected, and it has ends that extend indefinitely. So even though the ends are pointing in opposite directions, they do continue on in those directions, and the graph widens out, as you go from, negative infinity to positive infinity. And that kind of, that should make sense because the domain is all real numbers for any polynomial function, right? And so because of that, we're going to have ends that go to those infinities. With the second graph, looks like a little piece was chopped off in the notes here. We have a nice rounded hill, a nice rounded valley, another rounded hill. Everything's fully connected, and the ends, they continue on indefinitely. Looks like both are pointing down. And in the last one, we're seeing those hallmarks again. And we have a nice rounded valley, nice rounded hill, another valley, another hill, another valley. So this is kind of a wonky graph, but even though it's got a little more action going on in it, it still has the hallmarks of a polynomial function graph. It's fully connected, and the ends, of course, extend indefinitely. Some examples of non-polynomial graphs are in the second column. If we look at the graph at the very top, it does have some of the hallmarks of a polynomial function. Like, for example, it's fully connected and the ends extend indefinitely. But the issue with this graph, which does not make it a polynomial, is what's happening right here. Okay, that's something that we would call a sharp point. Also known as a corner. And polynomial function graphs won't have those sharp points or corners or those little kinks in the graph. If there's any low point on the graph of a polynomial, it should be part of a rounded valley, kind of a rounded out valley. Anybody want to tell me what would make the next graph the graph of a non-polynomial function? So the second graph in the second column. Yep, there's definitely a hole or an open circle. Has an open end. It seems like, the graph is fully connected other than that hole or open end. It also looks like one of the ends here extends indefinitely, but the other end of the graph doesn't extend indefinitely. It's as if the graph kind of stops right there, right? So that would be another reason why this is not the graph of a polynomial function. n does not extend. What do you think the issue might be with the third graph? Correct. Yep, not fully connected. This graph's broken up into two different pieces, and that would never happen with the graph of a polynomial function. Okay, does this kind of help out, help differentiate, you know, graphs of polynomials versus non-polynomial graphs? Getting the gist of it? So let's talk about an important concept regarding the graphs of polynomial functions, and that concept is known as end behavior, or EB for short. End behavior is what we, or I'll state it this way, when we focus on what the ends of the graph of a polynomial function are doing, we're describing the graph's end behavior. And maybe I can go back up to the table to illustrate this. If we look at the polynomial graph examples, the ends are kind of doing different things, going from one graph to the next. For instance, in the very top graph, we have one end of the graph that's pointing up, and we have the other end that's pointing down. And there's actually a reason why the ends of this graph, behave this way versus the ends of something like the second graph where they're both pointing down. And it has to do with both the leading coefficient and the degree of the polynomial function, believe it or not. And so, in the first graph, we've got one end pointing up in quadrant 1, the other in quadrant 3 pointing down. And then in the second graph, we have both ends pointing down. One's going in quadrant 3, one in 4. And then in the third and final graph here, we have both ends pointing up. So one end is pointing up in quadrant 1, the other up in quadrant 2. And again, the reasoning behind why all that's happening has to do with the leading coefficient and the degree of the polynomial function. So it says here, end behavior describes the direction in which the ends of a polynomial graph are facing. And there's really only 4 possibilities in which the ends can be oriented. And as it says here, they're all based on the leading term of the polynomial function, which, thinking back on page 1, leading term was this guy, a sub n x to the power of n. And I'm going to state a couple of facts about 2 pieces here. First, the degree. The degree is either even or odd. Okay, so there are 2 possibilities for the degree. As for the leading coefficient, a sub n, which is the other piece I want to look at, a sub n is either going to be a positive number or a negative number. And so each of these 2 values have 2 possibilities. And so just a quick principle of I guess probability. The total number of possibilities would be 4. You have 2 options for the degree and 2 options for the leading coefficient. And so it gives rise to 4 different types of these so-called end behaviors. And before we move on to the next page, sometimes it's hard to tell when you're being asked to provide an answer regarding end behavior. So I just made a little note down here as to what you want to look out for. in my math lab, it might ask you to, find the power function that the graph of f resembles for large values of absolute value of x. I think that is way too wordy, but it is what it is. The answer to something like this is really just referring to the leading term. So just a heads up. So I usually break down the 4 different types of end behavior into an end behavior chart. And you can see that I have 4 coordinate planes here. And I've broken down the rows according to degree. Okay, the first row refers to a polynomial function with an even degree, and the second row refers to a polynomial function with an odd degree. And then the columns are organized by the sign of the leading coefficient. In the first column, this refers to a leading coefficient that's positive, and then the second column is a leading coefficient that's negative. So we can kind of think of this as like a multiplication table, if you will. It's like in this first box, the upper left-hand corner, I'm going to draw out the end behavior for a polynomial function having both an even degree and a positive leading coefficient. So if your polynomial function has an even degree and positive leading coefficient, the ends of the graph will both be pointing up, one in quadrant 1 and the other in quadrant 4. As for what's happening between the ends, that'll kind of depend on the terms of the polynomial function, so we won't look at that just yet. Now, if the leading coefficient is negative, you can kind of think of this as like an x-axis reflection where the ends would be reflected across the x-axis and both point down. With an odd degree, if the leading coefficient is positive, you're going to have one end pointing up in quadrant 1 and the other end pointing down in quadrant 3. And if the leading coefficient is negative, you'll have one end pointing up in quadrant 2, the other end pointing down in quadrant 4. And a little trick here is just to note that odd starts with the letter O, and so does the word opposite. And so what I mean by this is that the ends are pointing in opposite directions. Okay, we have one pointing up in quadrant 1, the other down in quadrant 3, and then one in quadrant 2 and one in quadrant 4. So the ends point in opposite directions. And there are a couple of library functions that we can kind of link the end behavior to. For the even degree, my tip is think of this library function, f of x equals x squared. A quick sketch of x squared is what I'll include underneath it. Okay, it was a parabola, and x squared represents a function with an even degree, and as you can see, both ends are pointing up. And they're pointing up because the leading coefficient of something like x squared is a positive 1. For an odd degree polynomial function, with regard to the end behavior, my tip for you is to think of f of x equals x cubed. Okay, when we saw this in the library, a rough sketch of that is given right here. And as you can see, we have one end pointing up in quadrant 1, the other end pointing down in quadrant 3. And the reason for that is because we have an odd degree in conjunction with a positive leading coefficient. Is this all making sense so far? All right. Now on the right-hand side, just for sake of completion, you can think of f of x equals negative x squared for a polynomial function with even degree and a negative leading coefficient. That would cause the graph of x squared to flip upside down. In this case, both ends are pointing down. We have an even degree and negative leading coefficient. And then last but not least, for the last end behavior, you can think of f of x equals negative x cubed, in which case that would be an x-axis reflection of the graph of x cubed. And this would be a situation where an end points up in quadrant 2 and down in quadrant 4. And the reason for this end behavior, because of an odd degree and a negative leading coefficient. Okay, let's get to a couple of examples related to end behavior. The first example, multiple choice problem here. Gotta love that. Let's choose the graph that represents f of x equals, and here we have negative x cubed plus 5x minus 1. So it definitely fits the format of a polynomial function. It looks like x squared is missing, but that's okay. And the way to approach a problem like this is to look at the leading term, which our leading term is negative x cubed. And the important stuff about this leading term is the degree and the leading coefficient. The degree is odd, and the leading coefficient is negative. So based on our end behavior chart, when it's odd and the leading coefficient is negative, we're going to have one end pointing up in quadrant 2 and the other pointing down in quadrant 4. And so what I'd like you folks to do is look at the 4 options here and tell me which graph has an end pointing up in quadrant 2 and one pointing down in quadrant 4. Bingo, you got it. Okay, this end is up in quadrant 2 and this end is down in quadrant 4. Isn't that pretty cool how we can answer something like this just by looking at one of the terms? I'm going to have you folks try this one, kind of a different spin on it. This time they give us the graph and want us to select a function that would correspond to it. And my clue to you would be to look at the ends of this graph and see which option here would have a leading term that would give this end behavior. Any takers as to which function? Very good. Yep, the function in A. Here's the reasoning for that. Both ends are pointing up. That means that our degree should be even. I'll say degree equals even. And the fact that they're pointing up instead of down would mean that our leading coefficient, we'll say a sub n, should be a positive number. So any of these functions with odd degree can be ruled out, namely options C and D. Options A and B have the even degree, but the major difference between these two options is that option B has a negative leading coefficient, and that would give us a graph in which case the ends point down, so we can eliminate option B. And to confirm option A, we have the even degree of 4, and the leading coefficient is a positive 1. So, yep, very good. Option A. All right, one more topic before we take a break. And that would be turning points. Turning points are points on graphs of polynomial functions where the behavior changes from increasing to decreasing. And so let me give you a little sketch of this. Let's say that we're looking at a hill on the graph of a polynomial function. If we place our index finger here and trace from left to right, this part of the graph would be increasing at first until it reaches the very top of this hill, in which case going past it, the graph would be decreasing. So this is an instance where it goes from increasing to decreasing. The point at which the behavior changes, this is what we're referring to as a turning point, which I call TP for short. There's another name for this though, something that we discussed back in chapter 3. Anybody want to offer what they think a point like that might be? Okay, in the case of a parabola, that would be the vertex, yep. But going even more general than that, it would also be a maximum, wouldn't it? Yep. So likewise, we might have a valley as part of the graph of a polynomial function, in which case, we go from decreasing, reach a point right here, and going beyond that point, we go to increasing. That point, which is separating the two different behaviors, is also an example of a turning point. And generally speaking, or being more general about it, it's also minimum. So we're basically giving more terminology to our maximums and minimums. Okay, but the terminology turning points is more specific to polynomial functions. All right, so we can still have maximums and minimums on non-polynomial function graphs, but they're likely not going to be called turning points. This is more specific to polynomials. So turning points are where the behavior changes, and I'll give you a neat little fact about turning points. The largest amount of turning points that the graph of a polynomial function can have is given by this formula. T equals n minus 1. Okay, T represents the number of turning points, and n would represent the degree of the polynomial function. Now, in a lot of cases, you're given the graph of a polynomial function, and you have to determine what the smallest possible degree of the function is. And the way to answer that is to do kind of a rewrite of the formula I just gave you. The smallest possible degree of a polynomial function is something that we could kind of hone in on based on a graph in conjunction with the number of turning points. So I'm going to take this formula t equals n minus 1, and I'm going to solve for n simply by adding 1 to each side, and we would get t plus 1 is equal to n. So the smallest possible degree that a polynomial function could have would be given by the number of turning points plus 1. So t plus 1. And to wrap things up before our break, have a graph of a polynomial function here, and it says determine the function's smallest possible degree. In order to answer that, we need to look at how many turning points this graph has. Let's maybe start that out by seeing where the graph is increasing and decreasing. So going from left to right, starting at the left end of the graph, if you trace your finger along it, you get a part of the graph that's increasing until you get to what looks like an x-intercept here. Once you go past it, your graph decreases for a little bit. I probably should have blown this graph up a little bit more, but you decrease for just a little tiny bit, and you get to what looks like a local minimum, in which case you begin to increase until you get to what looks like an absolute maximum, and then the rest of the graph decreases from there on out. So let's look at these points where the behavior is changing. One point where the behavior is changing is right here. That would be an example of a turning point. We then go from decreasing to increasing. So that's a turning point. And then we go from increasing to decreasing. So 3, 8, randomly labeled, is also a turning point. So in this case, t is equal to 3. That's the number of turning points. So the smallest possible degree, I'll write it as n, would be what? Four. Yep. All right, and that's coming from this expression. The smallest possible degree of a polynomial function will be given as t plus 1, where t is the number of turning points. So 4 represents the smallest possible degree. All right, gang, that's a lot of info, and I hate to say it, but I've got more info coming your way after our break. And once we take care of the rest of 5.1, we will synthesize all this new material to analyze the graph of a polynomial function, which is what 5.2 is about. All right, so I'll see you guys in about 5 minutes. All right, folks, let's get back in the saddle here. One final note regarding turning points is that turning points are essentially the maximums and minimums of a polynomials graph. All right, because it's at these maximums and minimums where the behavior would change from increasing to decreasing and vice versa. We're going to move on to one of the most important topics regarding polynomial functions, and that would be the topic of real zeros. And real zeros are not necessarily going to be the number 0 itself, but rather real zeros are numbers that we could plug in to the function that produce an output of 0. And so in this definition right here, let's assume that r is a real number. And let's also assume that when we plug r into the function, the output is 0. So if this number r causes this to happen where the output is 0, then that number that we plugged in, regardless of its value, would be called a real zero of the function. Now, what's the big deal about having these numbers? Well, we'll see that on the next page. But first, I just want to just kind of prime you guys for what's heading our way. In this example, we have a polynomial function that's not written in standard form, but rather it's written in what I like to call like a partially factored form. I mean, if we wanted to, we could FOIL x plus 1 and then bring it in with x minus 3 through FOIL. But it just so turns out that this version of the function makes it a little easier to figure out what numbers can be plugged in to produce an output of 0. So I want you to look at the expressions inside the parentheses, maybe starting with x plus 1. Can you think of a number for x that would turn this into 0? Yeah, let's try f of negative 1. If we plug negative 1 into this function, you have to plug it in for x in both sets of parentheses. In the first set of parentheses, we get 0 squared, and in the second set, we get negative 4. 0 squared is 0, and 0 times negative 4 is 0. So negative 1 fits this definition, meaning that negative 1 is a real 0. Can anybody maybe think of another number that we could plug into the function to get an output of 0? Three. Yeah, so look at the second set of parentheses. If we plug 3 into the function, we're going to get 3 plus 1 quantity squared times 3 minus 3. That's 4 squared times 0, which is 16 times 0, and we get an output of 0. It turns out that these are the only two numbers that you could plug into the function to get outputs that are equal to 0. So to answer this question, the zeros are the numbers that got plugged in, negative 1 and 3. So real zeros are based on what they produce, right? Real zeros produce outputs that are the number 0. Okay, so it can be a little confusing, the definition. It's not what the numbers are, it's rather what the numbers do. Okay, so -1 and 3, what they do is they produce an output of 0, and that's why they're called real zeros. Now, the big deal about these numbers can be summarized in this graphic that I put together. It's kind of a little chain link here of results that you get once you know that a number is a real zero. This is considered a TFAE result, meaning the following are equivalent. And in plain old English, that means that if one of these facts is true, then all of the rest of them are true. So let's maybe start at the top. The first result says that R is a real zero. Okay, so if R is a real zero, then that would also mean that we could plug R into the function and it would produce an output of 0. So thinking back on that example that we just did, one of our zeros was -1. Okay, we saw that -1 is a real zero. I believe it was -1, right? Yeah. So since -1 is a real zero, it would mean that f of -1 equals 0. And we actually saw that when we worked out the arithmetic. It would also mean that that -1 solves the equation f of x equals 0. So we could say -1 solves f of x equals 0. Okay, it would be a solution to the equation that we can form by setting the function equal to 0. And this will be important for sections 3 and 4. It also means x minus that number is a factor of f of x. Now, in our instance, okay, x minus r would look like x minus -1. I'll put that in parentheses. And due to the double negative, the factor would look like x plus 1. And so if we wanted to factor our polynomial function from the last example, we would see that x plus 1 is one of the factors. And looking back at that example, that would be true, because in its partially factored form, we've got x plus 1 quantity squared. So naturally, x plus 1 would be a factor of this entire polynomial function. As for the rest of the factors, I'll just put ... because I just want to emphasize that x plus 1 would be a factor. And there's a natural consequence on the graph. The real zero is an x-intercept. So in other words, -1, 0 would be an x-intercept on the graph of the function f of x. So a lot of results here, and we won't necessarily have to use all of them at one time when working with a real zero. Usually it's just, okay, based on the information you have, can we jump to, one of the other results? So for instance, if we know that r is a real zero, then one thing we might be able to do is begin to construct the function that it's a zero of. Or if we need to figure out what the zeros are, we could look at the graph of the function and figure out the x-intercepts. The x-intercepts would help us identify the zeros of the polynomial function. Okay, so there's a variety of skills that we could do depending on the information we're provided and how we can jump to the information they're requesting. One instance of that would be in our next topic, where it says that we can create the factors of a polynomial function when given its zeros. So here's a classic example of that. It says here, form a polynomial whose zeros and degrees are given, and we're going to write the polynomial with integer coefficients and a leading coefficient of 1. That right there to me is kind of like lawyer language. That's usually the case when we solve something like this. The main crux of the problem is this part. Now, if you look below, there's a list of zeros, -2, 2, and 1. And there's also a statement about the degree that we should get when we're done with the problem. Our polynomial should have a degree of 3. My strategy on this I'd like to share with you is making what I like to call a zero factor table, much like an XY chart. In the first column will go our zeros, and in the second column will go our factors. Now let's list the zeros. You've got -2, 2, and 1. Now keep in mind that if r is a real zero, then the format of the factor that you can build is x minus that number. Okay, so let's start with -2. The factor associated with it would be x minus -2, which simplifies to x plus 2. What would the second factor be based on the second zero? X minus 2. Last factor? Okay, so if these are the zeros, then the factors of our polynomial function would be x plus 2, x minus 2, and x minus 1. And here's what we're going to do with those three factors. Let's write f of x equals, and we'll take x plus 2, we'll multiply it to x minus 2, and we'll then multiply by x minus 1. And this would be our polynomial function, and the format that it's in is what I like to call factored form. Now, factored form is nice, especially if it's given to you, at the start of a problem. We could figure out the zeros pretty quickly by looking at numbers that turn each set of parentheses to 0. But keep in mind that we need to verify that our polynomial has a degree of 3, and it's a little hard to tell when a polynomial function is in factored form. So when you have it written this way, there's a little bit more that you have to do, and that little bit more is foiling. All right, so we're going to multiply all these together, and the way to do it is by choosing 2 at a time. So for example, you might consider foiling x plus 2 times x minus 2. All right, can I have you guys do that? And then we'll see what to do with the x minus 1. Did you guys get x squared minus 4 for that? Okay. Let's keep this gravy train rolling. We'll now FOIL x squared minus 4 with x minus 1. Okay, let me have you work on that and make sure that you simplify and put it in standard form. And once that's taken care of, you should have your final answer. So I'll give you a moment to FOIL this out, and then we'll see how we did. All right, I'm getting x cubed minus x squared minus 4x plus 4. All right, Robert's getting that too. Everybody else getting this polynomial? Awesome. So this is our polynomial function in standard form. And the nice thing about having the function in standard form is that we can clearly see that the degree is 3. All right, so I swear this is the last of the topics regarding polynomial functions, last of the terms, so to speak, not last of the concepts, because that's what Chapter 5 is all about. But maybe the last of like the informational pieces for now. I know that's a lot of information coming our way in this section. So if at any point I'm losing you, feel free to chime on in, and I'll be happy to clarify anything. But you know, if you're like me, you're probably going to need like a half-hour nap after this class is over with today. I'm just kidding. So when discussing the topic of zeros, you typically see kind of a follow-up topic here on what's called multiplicity. And multiplicity just basically addresses any repeats of zeros of a polynomial function. And in simple terms, multiplicity essentially just keeps track of how many times a zero shows up as an answer to this equation, which is an equation that we saw in like that ring of results. And to shed some light on this, here's that polynomial function again, which we already found the zeros of, but we kind of did that mentally. I'd like to show you how to do it algebraically. So it says here, list each real zero and its multiplicity, and this will be kind of a common setup for the rest of this section, as well as the ones that are coming up, 2 through 4. Anytime that we're trying to find a real zero of a polynomial function and it's given to us in an equation format, we set up the equation by writing f of x equals 0 and then replacing f of x with the expression it's equal to. And this expression is almost fully factored. I'm going to put it in its full factored form by breaking up x plus 1 squared as 2 factors of x plus 1. Now, in the context of solving just an equation, which is what we're looking to do here, you guys remember what we would do with all the factors if they're multiplying to give us 0? Yeah, so remember, when we have one side that's fully factored and the other side is 0, then we can quickly solve for x by setting each factor to 0. And we solve these little micro equations, if you will, to get x equals -1, x equals -1, and x equals 3. So these are our zeros. They not only want us to identify the zeros, but they also want us to identify the multiplicity. How many times does -1 show up as an answer? It shows up twice. Because -1 shows up twice, we would say that it has a multiplicity of 2, which I'll say mult2 for short. How many times does x equals 3 show up? Shows up 1 time, so that would have a multiplicity of 1. Now, here's a little secret. If we look at the powers on the factors of the polynomial function, x plus 1 has a power of 2, and although it's not written, x minus 3 has a power of 1. So whatever 0 you get for the factor of x plus 1, which we saw as -1, the multiplicity should be 2, all right, which confirms our multiplicity down here. And whatever 0 we get for x minus 3, which we saw was positive 3, the multiplicity of that should be 1. So if your function is in like this partially factored form, then you can identify the multiplicity just by looking at the powers on each factor. Alternatively, you can solve the equation f of x equals 0 and then just count how many times each 0 shows up as an answer. Now, what's important about multiplicity is the effect that it has on the graph of a polynomial function. The multiplicity is either going to be an even or odd number, and any 0 that has an even multiplicity will correspond to an x-intercept at which the graph touches the x-axis. So zeros of even multiplicity are going to cause the graph to do what's called touch the x-axis. And I have a graph of that function that we just worked with just to illustrate what a touch looks like. Zeros that have odd multiplicity will cause the graph to cross the x-axis. So with zeros of even multiplicity, it's almost as if the x-axis is kind of like a little force field that the graph can't go through. But with zeros of odd multiplicity, the graph can go through that force field. In other words, it can go through the x-axis. So here's the graph of that function that we've been working with. And there are two x-intercepts. We have one right here, and we have one right there. And we actually know where these x-intercepts are at, just based on finding the zeros. This one is at -1, 0, and the other one would be at 2, 0. Now, to illustrate, what's happening, whether it's a cross or a touch, let's imagine tracing this graph from left to right. And I'm going to do it with my orange pen here. If we start at the left end of the graph, we're increasing until we get to this x-intercept. And the graph doesn't go through that x-intercept. It's as if, it's a little force field on the graph. What happens is the graph kind of bounces off the x-axis to head in the other direction. And then when it comes up to the second x-intercept, the graph goes through it. So the x-intercept at which the graph did not go through the x-axis, that would be an example of a touch. And then the x-intercept at which the graph crosses the x-axis, that would be an example of a cross. Does that make sense? Everybody else? All right, cool. Okay, so to the last example of this section, we're going to construct a polynomial function based on this graph. And I'm going to tie a lot of our recent concepts in to help us with this solution. So we're looking for the equation for f of x. And we can start to build the equation by first looking at the x-intercepts, because based on that ring of results, maybe I'll call it the infinity stones there, any x-intercept is going to correspond to a 0 of the function. Now, how many x-intercepts are we seeing on this graph? We've got 3 of them. Yep. Perhaps I'll do this in a table format. There are going to be a few columns in this table. The first column will consist of the x-intercepts. Okay, and I'll write them out as ordered pairs. What is the ordered pair for the x-intercept furthest to the left? -5, 0. All right, the middle x-intercept, -3, 0. And the last x-intercept, 0, 0. You got it. You guys are lighting up the chat. I love it. Now, each one of these x values from the x-intercepts is going to correspond to a real 0. So in this next column, we'll just populate it with the x values from these ordered pairs, -5, -3, and 0. I also want to tie in multiplicity. And then that'll help us to build our factors. Now, what's happening here at -5? Would that be a cross or a touch? That would be a cross. Yep. So since it's a cross, we can assume that -5 has an odd multiplicity. Let's start with a multiplicity of 1 for that. And I'll explain why I'm using 1 versus 3, 5, 7, and so on and so forth. But first, let's look at what's happening now with -3. Okay, would that be a cross or a touch? You sure? Yeah, it would be a cross. Yep. The graph goes through the x-axis there. So another instance of odd multiplicity. Let's put 1 for that. And then what's happening at the origin? Cross or a touch? That's a cross. Okay, so odd multiplicity, we can use 1 for that. And what we'll do to build the factors, keep in mind it's always x minus the 0, so x minus -5. And I'm going to put the multiplicity as the power on this factor. And then cleaning that all up, this results in the factor x plus 5. The second factor would be x minus -3, and I'll put the multiplicity as the power. And that simplifies to x plus 3. And then our last factor, x minus 0, put the multiplicity as the power, and that all simplifies to x. Now, the reason why I'm using 1 for the multiplicity here has to do with the fact that there are 2 turning points. We have a turning point up here in quadrant 2, and we have a turning point in quadrant 3. So in terms of number of turning points, there are 2. So the minimum degree would be given by that formula t plus 1, which is 3. So this graph has to correspond to a polynomial function with a degree of at least 3. And the multiplicities, if you add them all up, they add up to this number 3. And so that's why I'm choosing to use a multiplicity of 1 as the odd multiplicity versus anything like 3 or 5 or 7. And that's kind of the trick as to, you know, what multiplicity to use. Look at the minimal degree. The minimal degree is 3. And then just check your multiplicity values and make sure that they add up to that minimal degree. Does that make sense? So last but not least, you will take these factors and multiply them out. Okay, this would be the factored form of our function. Can you guys go ahead and FOIL this all out? And in about, I don't know, a minute or so, I'll provide the standard form version.